So this is a graph of the derivative of some function. We need to find out where the function is increasing. These are all negative slopes. Negative slopes. It means that every instantaneous point, this is a slope of 0 here, but every other slope here is negative. So it's decreasing for all these places. The only place where the slopes are positive of the original function are here. So from -3 to -2, it's increasing. For part B, we need to find the x-coordinate for points of inflection. Just remember that an inflection point is where there is talking about where the rate of change of the slopes changes from positive to negative. So it's talking about where the direction of the slopes of how the slope is moving changes from positive to negative. So everywhere in the graph of the derivative, we want to find out where the slopes go from decreasing to increasing, and that's an inflection point. And right here, we went from decreasing to increasing slopes. So that's an inflection point at x equals 0. And our slopes were increasing, and then they started decreasing. So at x equals 2 is another inflection point. So to find an equation for the line tangent to the graph of f at the point 0, 3. Remember, tangent line is just a straight line that intersects at one point on the graph. So we don't know what the original graph of f is, but we can still find its tangency equation by finding the slope from this graph up here. At x equals 0, our graph tells us that the slope is -2. Because again, the y values that are being spit out of this graph are instantaneous slopes. So at x equals 0, y equals -2. So we have our slope, it's -2. So to find the constant b that we need here, you just need to plug in 0, 3. Plug in 0 in for x and 3 in for y. And now you have something to solve. I think it's actually pretty clear that y-intercept's 3 because the y-intercept's where it crosses the y-axis. So y equals -2x plus 3 is our final answer there. So D wants us to find exact values from the original function. And what we can do is we can take the point that we were given here, 0, 3 is on the graph. And then we could find the integral of the area between -3 and 0 on the x-axis to find out how much we've changed in location. Because the integral of the derivative function brings you back to the original location function, f. And if you integrate and find out exactly how much location has changed between -3 and 0, because again, integrating f tells you how much you've changed. That will tell you the total amount of distance you've changed from 3. Okay, so to find this area under the curve, we don't have the original function to use the fundamental theorem for. But what we can do is use area. The area between here and here is a negative area, and it's just the area of a triangle. So that's, we got to make sure we put the negative sign for negative area because it's under the x-axis. That's a -1/2 because it's 1/2 base times height for that triangle. We need to add to that the area change that's happened between -3 and -2. So that's another triangle. It's 1/2 base times height. So we've changed a total of -3/2. That means going from x equals 3 to x equals 0, we've gone backwards -3/2 in our original location because, again, the integral of velocity is the location function. So we started at 3. We backed up 3/2 spaces because it's -3/2. So to get us back to where we started, we got to add 3/2. Okay. So at x equals, we're at the location of 3 because that's the y coordinate that we have for the first one. And then if you add 3/2 to it, because again you're backing up, you're going in reverse direction, so minus a negative there. You get 6/2 plus 3/2. That's 9/2 for your original location. Okay. You can do something similar to find out f of 4. You can take the integral from 0 to 4 of the derivative function, because that will tell you how much your location has changed. This is a little trickier because what's the area under the curve? Here and here. It's not as easy as triangles, but what you can do is you can use the radius. This is a radius of 2 circle. So the circle is in total, the semicircle actually I should say, I'm going to take half a circle. Half pi r squared. So 2 squared gives us 4. That's the area of that circle, but if we were to consider the entire rectangle, the area should be 8. So 8 minus our 2 pi is going to give us that total, that blue shaded area. And again, with that calculation, I took the area of the whole rectangle, which is 8, and I subtracted out the area of the semicircle, which we found to be 1/2 pi times 4, because it was 1/2 times the area of the circle. And so that leaves you with the amount of change that's occurred between 0 and 4. So if we start at 3 for a location, then we went positive, and then we increase this amount in distance, 8 subtracted by 2 pi over 4. We just have to add the two quantities. Nope, one quick thing I missed. So this is the correct for the area over here, but this is negative area because it's under the x-axis. So it's got to have a negative sign out front of it. Okay, but still the same idea. We start at 3, and we're going to add to it our the negative area to show how much we've changed. So this will give us our final location, -5 plus 2 pi. Okay, and that's it for this one.